Okay, so last time we started this section 8.3 over trigonometric integrals. And what we discussed last time were integrals with functions of this form. So we have powers of sine times powers of cosine. And I taught you, I guess it was 3 different strategies, depending on whether the powers were even or odd. So there's a strategy if n is odd. There's another strategy if n is odd. And if neither of them are odd, we had a third strategy. If you have odd powers, the basic idea is to use the Pythagorean theorem to convert even powers of cosine or sine into their opposite trig function. So if you have an odd power of sine, you would break off the even part, leaving one behind, and convert the rest of them to cosines. And the opposite works for cosine being odd. So that was, I guess, the first couple pages there. And then the third strategy applied when both powers were even, like this one, we have sine to the fourth and cosine squared. And for this, you'll have to use a different formula. This is sometimes called the double angle or half angle formula. And you convert everything into sines, you convert everything into cosines, as you can see here on the right side of both of these formulas. And then, well, there's a process of trying to simplify things and work things out that we saw last time. So these tend to be a little bit more challenging when everything is even. There's oftentimes a little bit more work to do. So that's what we did last time. Today we're going to start with this little trick that sometimes works to, this little trick that sometimes works to get rid of square roots in integrals. Like this integral, you want to integrate the square root of 1 minus cosine of 8x, but we don't have any rules, of course, in our table or in the rules that you have memorized involving square roots of trig functions. So the first thing that we should do is try to get rid of them, the square root, in order to figure out something that will actually work for us. And for this particular kind of problem, we're going to return to the same formulas that we used for even powers of sine and cosine, except we're going to rearrange them slightly. So basically, I'm going to multiply the cosine rule by 2 on both sides to get this new formula. 2 times cosine squared, or excuse me, there's a minus sign, so we need the other one. Two times sine squared of x is equal to 1 minus cosine of 2x. And the opposite rule, which I guess I might as well write down, for 2 times cosine squared would be 1 plus cosine of 2x. So these two rules, rearranging the formulas from the last section, the last problem a little bit, these two formulas can help us with problems like this, because when you take a square root of a function squared, well, we can get rid of the square root most of the time. So there is a little bit of subtlety here. We have a cosine of 8x, and in the formula, we have cosine of 2x. So we're going to have to think of this as being 2 times 4x. And 4x is going to play the role of x in the formula here. So when we use that first formula, we'll get 2 sine squared of 4x instead of just a single x. Like this. So with this substitution using the formula, we're now taking the square root of a function squared, which means we can get rid of the square root, but we do have to worry a little bit about whether sine is positive or negative. So what I mean here is there's this little subtlety that we don't normally have to think about, or we don't have to think about very often. But when you take the square root of x squared, you're actually looking at the absolute value of x, because square roots are always positive. Or at least, let's see, I should say always greater than or equal to 0. So you're really looking at an absolute value of this sine function. For this particular problem, we'll see in a second how to handle that. So we're looking at the absolute value of sine of 4x. For this particular problem, it's a definite integral from 0 to pi over 4. So in order to deal with the absolute value sign for sine of 4x, we have to think about where on the unit circle we're going to be. So what do you think? 0 to pi over 4 for sine of 4x, where are we going to be on the unit circle? Where are our values of sine going to come from? You do have to think a little bit about this 4, because when you multiply 4 times a value between 0 and pi over 4, that's going to determine where you are on the unit circle for your value of sine. But for this particular one, we're sticking between 0 and pi over 4, and when you multiply by 4, that's 0 to pi. So we're going to be looking at the upper half of the unit circle, and we know that the sine function is always greater than or equal to 0 on the upper half of the circle. So in this particular case, we can actually just drop the absolute values. But that is something you have to think about, because if we were on a different part of the unit circle, we might have to put a minus sign or something like that on our integral. So let's write this down without the mess, because we do know how to do the problem now. We just have a constant times sine of 4x. There's a small u substitution that we need to do. U equals 4x, the inside of the sine function. And then du would be 4 dx, which means we'll have to divide through by 4. Okay. So you don't have to write out this u substitution if you know how to do it in your head, if you know how to get the 1 over 4 that we'll need in the problem. So let's do that. Let's see, so we can just go ahead and do the whole thing. The antiderivative for sine is minus cosine. We already talked about that earlier. So we'll actually get a minus square root of 2 over 4 cosine of 4x. And I lost my limits of integration on the last step, but they will be important here at the end. Okay, so now we need to plug in our limits of integration and find the difference. Let's leave this constant on the outside. We need cosine of 4 times pi over 4. That's cosine of pi. And we subtract cosine of 0. Cosine of pi, that's the x coordinate over here, remember? So that's 1 or minus 1. And then cosine of 0 is the x coordinate over here on the unit circle. So that's positive 1. So we have minus 1, that's a minus 2. And then we have an extra minus sign over here, and we can cancel with the 4 in the denominator. So overall, we get a square root 2 over 2. So just working through the arithmetic quickly there at the end. Does anyone have questions over that problem? Okay, so since it doesn't seem like you guys have any questions, let's move on to the last part of the section. We're going to look at powers of tangent and cotangent, like we looked at powers of sine and cosine last time. And let's see, I think I have 3 examples here for us, just to demonstrate the kinds of strategies that you can use. Put this page out of the way. And for powers of tangent, and there's a mistake here. We're actually only going to talk about powers of tangent and secant. Not really a big deal. Because the formula that we're going to use is this one. It's another version of the Pythagorean theorem. It says tan squared of x plus 1 is equal to secant squared of x. So just like we were able to convert even powers of sine and cosine back and forth, we're able to convert even powers of tangent and secant back and forth. Okay, so the first problem, we have an even power of tangent. So the idea here on this particular one is to split off a tangent squared and convert it using the formula into a secant, or a secant squared in this case. And you'll see why we might want a secant squared in just a second. It's going to help us with a u substitution. So tangent squared is going to be secant squared minus 1. So moving this 1 to the right side of the Pythagorean formula. So leave the first tangent squared there, and the second one becomes secant squared minus 1. Okay, so you might remember doing integrals with powers of tangent and secant squared because this is a simple u substitution. So the first half when we distribute is going to be, I guess, the easy half, you might say. So we'll break that off into an integral. and then we'll break off the second half. We'll have minus the integral of tangent squared. Okay, so here we have a u equals tangent, and then du will be secant squared plus the next there. So this one is straightforward. We have a u squared, so its integral is 1/3 u cubed, so that's a tangent cubed. The second one, we're actually going to do this substitution a second time. So our tangent squared is going to become secant squared minus 1 again. And now we can finish it off because we know the integral of secant squared is tangent, and an integral for 1 would just be x. So we get a minus tangent, and then there's 2 minus signs, so we get a plus x plus a constant. So if you have an even power of tangent, this is the strategy that you're going to use. You're going to successively break off tangent squared and substitute n using the Pythagorean theorem, and just keep on going until you're out of tangents to substitute. Okay, any questions over that example? Okay. So let's see what happens when we have even powers of secant. Well, you might expect we're going to do something similar, and we are. Maybe I'll write down their formula again, that we're using tan squared of x plus 1 equals secant squared of x. And this one actually I think is a little bit simpler. The idea behind this integral that we're about to do with an even power of secant is that secant squared is the du if we're going to do a u substitution with a tangent. So we want to break off a secant squared and leave it, and then what's left over is going to be another even power of secant, since we started with an even power. So what I mean is something like this. We'll have a secant to the 4th times a secant squared. So this secant squared we're going to leave alone because it's going to eventually become a du. And these other powers of secant I want to convert into tangents, which will become my u in my u substitution. So remember, a 4th power is really a squared squared. Maybe I'll cancel that off and rewrite this as secant squared squared. So I'm actually going to have 2 copies of this, or 2 factors, maybe is a better word. So we have tangent squared plus 1 for my secant squared, but that's squared. And then bring down the factor of secant squared that we want to leave there for our u substitution. Then we have to multiply out in order to finish the integral, we have to actually square things out. So if you wanted to use the FOIL method, if you need to think through all the terms and how they get multiplied, you might want to rewrite it. Tangent squared plus 1 is really tangent squared, excuse me, tangent squared of x plus 1 squared is really tangent squared of x plus 1 times tangent squared of x plus 1. So what we get is a tangent to the fourth plus 2 times tangent squared plus 1, and then secant squared is going along for the ride here. Now we can do our u substitution. We can do this one probably mentally. Our u is going to be tangent. Let's see, do we have some space over here? Yeah. And if u is tangent, then du is secant squared dx. So this last part of the integral, the secant squared x dx, is now our du. And here we have a u to the fourth plus 2u squared plus 1. So our answer will be 1 to the fifth. Increase the power on tangent. 1 over 5, excuse me. I might have said 1 to the fifth. Here, for our 2 tangent squared, we'll have to divide through by 3. So 2 over 3 tangent cubed. And then finally, here we just have a 1, but remember, we have this du on everything, the secant squared. So this is really a single tangent. And then plus c. And that's it. That's the integral. Any questions? Okay, so if you don't have any questions, then we'll move on to my last example here of what happens when you have powers of secant and then odd powers of tangent. So there are some other combinations of odd and even powers that you might have to think about on the homework, but this is the last one I'm going to do in class. So what should we do when we have an odd power of tangent and any power of secant? This one, we're going to break off a secant and a tangent. And then you'll see maybe in a second why we did it. So if I break off one power of each, what I'm left with is a secant cubed and then a tangent squared. And then I can write down my power, my single power of secant and my single power of tangent. Okay, so you can see what I did. I broke off a secant tangent. The idea here is that I'm eventually going to do a u substitution for secant, in which case my du would be a secant tangent, a secant x times tangent x. So this that I broke off is eventually going to become my du. But in order to use this idea, I'm going to have to convert this even leftover power of tangent into secants using this same formula that we used earlier. So I'll have to move this one to the right-hand side in order to get powers of secant. Okay, so let me write that in. This power of secant we'll leave alone, and then the tangent squared becomes secant squared of x minus 1. And then we bring down this factor that's going to be our du in a minute, the secant times tangent. And before we can finish off the integral, we'll have to distribute here this secant cubed into the parentheses, which gives us a secant to the 5th power of x minus secant cubed. And then bring down the rest. And now is where we can finally do our u substitution. So this is going to be a u to the 5th minus u cubed, and this is our du. So now it's a simple power rule problem. We increase the power by 1, divide by the new power. So that's 1 over 6 secant to the 6th power minus 1 over 4 secant to the 4th power. And then always remember to add your constant on the end. Any questions over that third example with powers of secant and tangent? Okay, so since it doesn't seem like you guys have any questions here either, this is our stopping point for section 8.3. And your homework is already posted to MyLab Math, so make sure you take a look at that. And I definitely encourage you to work on this one earlier than later, because as you've seen, as I've worked through examples, sometimes it can take a bit of time to work through the problems just because there's so much distributing and substitutions and that sort of thing that you have to do. So please work on this early and ask any questions that come up in class next week, or send me an email. Okay.